Assalamu alaikum students. Today's our topic is going to be about simple harmonic motion and circular motion, and how can we convert circular motion to execute simple harmonic motion. Now in this case, first of all we have to discuss displacement, velocity and acceleration. As you have seen that the body was executing a circular motion, and now we are going to compare it with a mass which is attached to a spring which is hung under the action of gravity. Now as the mass moves in a spring system, the circular motion is moving along it to the maximum point and to the minimum point and back to its original position. Now, if we draw a graph, then we can see that the displacement is minimum at the mean position. It is maximum at the extreme position. Again, it got back to its mean position, and then extreme position, then got back to its mean position again. Now, as the whole vibration and whole round trip was completed, let's assume that the body moved from its original position, let's say from point O1 to a new position, let's say point P, and the center of the circle, let's call it O. Now, in this case, we have a displacement done over here. Now, if we are talking about the displacement, let us first of all break it into parts. What parts? Horizontal and vertical components. The first part we are talking about the vertical component, which is right over here. So the same displacement as that of the mass attached referencing system, but it is not quite the height which we are looking for, which is x naught. So this height is basically taken as, let's say, x, and this much distance from here to here, let's call it y. And the angle which they both make with the hypotenuse, which is r, let's call it theta. The point at which they both meet the horizontal and vertical component, let's call that point n. Now in this case, we have seen the diagram now that this was a simple triangle, which is right angle triangle. This point is n, this point is p, this point is o, this is theta, this is x, and this is r, or you can say x naught, because both of them are equal, because of the amplitude is equal to the radius of the circle, as you can see over here, and this is equal to y. So now we are only concerned with the vertical part of the circular motion, because we are concerning the vertical mass attached to a spring system. So here we have the vertical component of r, which is x. So how can we basically arrange them in a scientific manner by a trigonometric formula, which is sine theta is equal to perpendicular over hypotenuse. Here the perpendicular is x and the hypotenuse is r, or we can rewrite it down as x is equal to r sine theta. So as you can see over here as well, this graph is basically executing the sine formation, that it is minimum at 0, maximum at 90, 0 at 180, maximum but in opposite direction in 270, and 0 at 360 again. Now referring to the diagram which is over here, let us clean this up a little bit so that you can see it clearly. It is talking about this diagram right over here. From time 0, the instant p passes through point O1, which is right over here. The angle which the radius OP sweeps is t, which is 0, 1, and OP is equal to theta. That means this angle which is taken to be taken by us, which is this line, which is O1, O and P, and this angle is basically theta. And this theta can be represented by omega t, where omega is basically what? Omega is the angular velocity, which is defined as angular displacement divided by time. The displacement on x on n at time t will be given as, this x is given as np, which is right over here. So np is equal to op sine angle of 1 op. That means in simple words, we are talking about this triangle P O and N over here, and this is angle theta. So this angle is basically this theta we are talking about, which is O1, which is over here, O and P, which is representing theta. Let us clear this out so there is less confusion. So let us write it down in the simple form. The x will be x written as it is, and P is basically OP is the radius, and sine theta is basically the angle O1, O, and P. We can rearrange it and we can write it down as x over r. Let us call this equation A. And this can be used in velocity as well as in the case of acceleration. This will also be displacement of the pointer P at instant t. The value of this x as a function of time is shown in figure. This t is the waveform of SHM. That means this circular motion is basically mentioning the simple harmonic motion in the form of graph. In the same waveform was traced experimentally, but here we have traced theoretically by linking simple harmonic motion with the circular motion. That means we have compared the simple harmonic motion with the circular motion and we have obtained the same graph. Through the concept of angular velocity, which is omega, the angle theta gives the state of the system vibration cycle. For example, the start of the cycle is 0. That means in the start, it was 0. When the quarter of the cycle was complete, the vibration was 90 or pi by 2, which was over here, the maximum displacement from the mean position. Half of the way through the cycle is 180. That means at this position, it got back to its mean position where the radian was pi. When theta was 270 or 3 pi by 2, it reached to the other point or other destination opposite to the original one, which was 3t by 4 time. The cycle is 3/4 completed. The theta is the phase of the vibration. That means it can be high, it can be low, it can be in any direction, as well as displacement from the mean position. Thus, the phase is also related with the circular motion aspect of the simple harmonic motion. That means the circular motion is also representing the simple harmonic motion according to this displacement concept, which is shown in the form of graph. Velocity. Now let us talk about velocity. As you can see, the body is moving in a simple harmonic motion as well as in circular motion, and we are now comparing them both as the body moved from extreme position to the mean position, back to the mean position again after going from the extreme position. Now we are concerned with velocity in this case. This was the displacement part. Now we are considering a time period in which was basically in between 0 and t by 4. Let's assume that the velocity in this case is making a tangent with the circle at this point. This is the velocity v which we are talking about. This velocity v is making a tangent, so it is making a 90-degree with the radius also. So this is the angle between the radius and the velocity, which is 90. Now, if we want to make this velocity into its components, let us divide that into its components. First of all, the horizontal component, let's call it Vx, and one vertical component, which is Vy. If we consider this line also, which was O, the original point, and the body moved to a new position, let's call it P again from the displacement. Let me clear that out a little bit. This is point P, and this is the center point O, and this was making an angle theta over here, and this is point N. Then this angle over here will also be theta, because we know that alternate angles are equal to each other. So if this is theta, then this will be equal to theta because of alternate angle. Now, if this is alternate angle, then how much will be this angle? This angle will be equal to 90 minus theta. Let me write down that again. So it will be equal to theta. Now, if we want to draw this triangle again over here so that it is clear for us, let me rub this off over here, the alternate angles part. Here we have the velocity. Should draw it with the red line so that it is quite similar to the diagram which we have drawn over here. So the velocity is over here, which is represented by V. There are two components. One is vertical, let's call it Vy, and the other component which is Vx. And this is the angle 90. Let me write down that again as well. So this is angle 90 minus theta. So again, we are now considering only the vertical component, and here the vertical component is Vy and of the velocity V. So any function which is representing the vertical component as the perpendicular and hypotenuse together, that is sine theta is equal to perpendicular over hypotenuse. But over here, the angle theta is given by 90 minus theta is equal to perpendicular is Vy and the hypotenuse is basically V. Now, if we look at this formula and we compare it with this formula, which is sine alpha minus beta, which was equal to sine alpha cos beta minus sine beta cos alpha. So if we put in the values in this equation, what do we get? Sine 90 minus theta is equal to sine 90 cos theta, where 90 is the angle, minus sine theta cos 90. As you can see, the cos 90 is equal to 0. So everything in this term will be equal to 0. And sine 90 will be equal to 1. So the only thing which is left now is cos theta. So we can say sine 90 minus theta is equal to cos theta. So we can now write it down as over here, where cos theta is equal to Vy over V. This is the whole concept of how cos was basically playing part in this whole case, that we can write down like this: V is equal to cos theta into Vy is equal to V cos theta. And this is why we are now going to write it down like this. Let's clear this out. Reconsidering the figure, let us reconsider the figure again, that we consider the velocity in this direction, which is was making the tangent line 90 degree, and we have converted them into its two components. One was vertical, the other one was horizontal, which is Vx over here and Vy over here. And this is the angle we call 90 minus theta, which was taken out to be cos theta is equal to Vy over V. Resolve the velocity of the body into its components. So we have two components. One was Vx, which was equal to V sine theta, and Vy was equal to V cos theta. Just by over here, we have proven this derivation, and we are only going to take this one because now we are only going to take the vertical component of the circular motion. As P vibrates, the direction of Vy, so we take only Vy only, because now we are comparing only with the vertical component of simple harmonic motion, because it is basically vibrating vertically. That is why we are taking Vy P cos theta. Here we are. Let's call it equation number 7.6. And this equation basically helps us to derive other equation as well. Let's continue. By trigonometric formula, we know that cos square theta is plus sine square theta is equal to 1. Let's rearrange it. It will be sine square theta is equal to 1 minus cos square theta, or we can say as well that cos square theta is equal to 1 minus sine square theta. We can also write it like that. Now, as we know that from figure that x over r is equal to sine theta, where we have done that, do you remember equation number A? If you don't, let us revise that part as well, which was done in the displacement. As you can see over here, this was the equation which we called equation A in the case of displacement, which is x over r is equal to sine theta. Let us go back to our derivation. Figure shows that x over r is equal to sine theta. So let us put this value of sine theta, which was basically in this formula, that cos square is equal to 1 minus sine square theta. So putting the value of sine in this equation, it will be cos square theta is equal to 1 minus, instead of sine, we are now writing down x square over r square. So here we are going to write down x square over r square, and here it is, cos square theta is equal to 1 minus x square over r square. Moving on, if we basically take under root on both sides, it will be cos theta is equal to under root x r square over r square minus x square over r square. What we have done over here is we have done cos theta is equal to 1 minus x square over r square, and we have taken the under root on both sides. So this square cancel out with this under root. It will be cos theta is equal to 1 minus x square over r square. So we are taking the LCM. So we have to multiply by r square and divide by r square minus x square over r square. It will be equal to, if we take it common, r square minus x square divided by r square, which is equal to cos theta. Here we are, cos theta is equal to under root r square minus x square divided by r square. Let's proceed further. Now we have taken r as outside the under root, because cos theta is equal to 1 r square minus x square divided by under root r square. So we cancel out this square with this under root. What we are left with, cos theta is equal to 1 over r into under root r square minus x square. Putting values of cos theta in equation 7.6, we call this 7.6. Let's put this value in this equation, and we got Vy is equal to V1 over r under root r square minus x square. Putting the values of V is equal to r omega in this equation. So we put the value of V into V over here. V is equal to r omega, where V is the angular velocity, r is the radius, and omega is the angular velocity. And angular velocity, which we have already done, is defined as angular displacement divided by time. Now, if we basically proceed, we will put the value of V equal to r omega, this small r with this r cancels out. What we are left with, V y is equal to omega under root r square minus x square. Now, how can we prove this one, that where will the velocity will be maximum and where will be minimum? Now, for that case, let us consider the maximum case. Let's say the velocity is maximum at the mean position. So for that, let us use this formula, V is equal to omega under root r square minus x square, and at mean position the value of displacement is equal to 0. So V max, V will be equal to omega r square minus 0. So V max will be equal to omega r square, this under root and this square will cancel, and V max will be equal to omega r, which is the maximum velocity of that body. That the maximum velocity of the body will be at the mean position. And what about the extreme position? Let's check about that. Again, using the same formula. Now we are talking about the mean position, or mean velocity actually. Omega under root r square minus x square. So the extreme position x will be equal to r. So V minimum will be equal to omega r square minus r square. So r square minus r square will be equal to 0, and 0 multiplied by omega will also be equal to 0. So it is the minimum velocity which is at the extreme position on either side of the oscillating body. The velocity will be minimum. And this is the graph of the velocity which we have drawn, which is a cost graph, which is right over here, that it is maximum at the mean position, it is minimum at the extreme position, it is maximum at the mean position again, it is minimum at the extreme position, and it got back to mean position again, and it became maximum. where r is the radius of the circle, x is the displacement of the projectile p of the mean position O, and omega is the angular velocity of the projectile particle p. Now we are talking about acceleration over here. Now, as you know, the body is moving in the circular motion, and it is compared with the mass attached to a spin system, which is oscillating up and down. Now, as the body is moving in the circular motion, so it must have a centripetal force acting on it, which is F is equal to MAC, where AC was given as V square over R, if we remember that formula. Now, this is a very important formula, and as we know that we are only considering the time period between 0 and t by 4, in that case, the acceleration is a centripetal acceleration, and it is moving towards the mean point, or let's say the center point. So AC is moving towards the center point. And now we are basically again moving the body from point O1 to point P, and the center point is O. Let's convert this as well in its components. So this is A, which is the vertical component of AC, and there is another component which is AX, which is the horizontal component of AC, and it is making an angle of theta as well. Now again, we are now concerned with this one. First of all, let us talk about the acceleration part. AC is equal to V square over R. Now, in this case, we know that V is equal to R omega because we want to convert the velocity into angular form. Putting this value in the above equation, it would be AC is equal to R whole omega, or we can say R omega whole square, like this, divided by R. So it will be R square omega square divided by R. This R and this square cancel out. What we are left with, A will be equal to R omega. So this AC will be equal to R omega. This we have concluded, and we will write it down over here. Let us rub it off and write down over here that AC is equal to R omega, and we will use that later on. So here's our derivation, that AC is equal to R omega. We have kept it on the side so that we can use it later on. Now, in this case, we have a diagram also, and this angle also. Now we have to also remember that the displacement was basically in the outward direction. Like in this case, it was in the outward direction. X was outward, or R was outward, X naught was outward, but the acceleration is towards the center. This is the main point which we have to understand in this condition. When the point P move on the circle, it has acceleration AC is equal to X into omega, which is the maximum displacement. So we put X naught over here, always directed towards the center of O of the circle. That means this is the point which is going to mention the acceleration will be towards the center of the circle. At instant T, the direction of will be along PO. That means this is point P and this is point O. The acceleration will be towards the center always. The acceleration of the point N will be the component of the acceleration along the diameter DE. That means we are going to, if we, this is a diameter D and E, which is moving from here to here, we are only taking the vertical component, which is A over here. So let us draw the diagram again. This is the AC, and we are only talking about A in this case because we are only talking about the vertical component of the acceleration, which is moving towards the center. Due to the motion of P as shown in figure, the value of the component is given by A is equal to AC into sine theta. That means these are two components of a triangle. One is perpendicular and the other one is hypotenuse, and the sine theta is equal to perpendicular over hypotenuse. So A over AC, or we can write down A is equal to AC sine theta. Putting that in the above equation, what do we get? And we also find out that AC was equal to R omega, or X naught omega, because the X naught is the maximum displacement from the mean position, which is equal to the radius of the circle as well. So that is why we can put R omega as well as AC is equal to X naught omega. So it's the same thing into 2 sine into omega square and sine theta, which is right over here. Let us rub it off now. So we have gotten our values over here. So X naught omega 2 sine theta omega square sine theta. Moving on, thus the acceleration will be n along the end point. This point is known as AC sine theta is equal to x naught omega square sine theta. So this is basically the acceleration at any instant which we have to find out. So it is a sine function and it is opposite direction to the displacement. Its direction is from n to O, that means from n point to O point towards the center point. Let's say from here to the center point, and NP and O divided by OP, which is N is this point and P is this point, and P divided by OP is given to us as x over x naught. Therefore, A is equal to x naught square is equal to, what is the value of cos theta? Oh, sorry, sine theta. We have to remember the displacement part again. In displacement, we have mentioned it as the sine theta was equal to x over r. So we are going to put x over r, or we can write it down x over x naught. So because we know that x naught is equal to r, because the maximum amplitude which a body can have in the circular motion is the radius of that body. So acceleration will be equal to omega square into x naught into x over x naught. This x naught and this x naught will cancel out. So what do we get at the end? This is acceleration at any instant depending upon the displacement, which is over here, x, and omega, which is a constant value. So A is equal to omega x, but we have to remember that the acceleration was towards the mean position, whereas the displacement was towards the circumference of the circle. So both of them were in opposite direction. So if they're in opposite direction, so we write down them in the form of a negative sign. Comparing the two figures show the direction of the acceleration and displacement are opposite. Considering the direction x as a reference point, the acceleration will be represented as a minus omega square into x. That means acceleration is directly proportional to the displacement, but in the opposite direction. This is the main feature of a simple harmonic motion, which is executed by the circular motion as well. And this graph is basically showing that the acceleration, as you can see, although it is directly proportional to the displacement, but in opposite direction. At the starting point, the displacement was minimum, so the acceleration is also minimum. At the extreme points, the acceleration is also maximum, the displacement in also the maximum, but in opposite direction. Again, at mean position, they both are having the less value, and extreme position, they are both opposite in direction, and their phase difference is 180, as you can see over here. And last but not the least, they came back to their original position, and the acceleration and the displacement became 0 again, which shows that acceleration is proportional to the displacement and directed towards the mean position, which is the characteristic of SHM. Thus, the point n execute SHM with the same amplitude and period and instantaneous displacement as that of the point P. This confirms that the exertion, the point of n, is just a replica of pointed motion, which shows that simple harmonic motion does execute in circular motion as well. I hope you understand today's lecture. Inshallah, will join us with another lecture. Allah Hafiz. Bye bye.